And tonight's presentation is by Marnie Berenson. And she's going to talk to us about star nurseries and October skies. So take it away, Marnie.
Okay. Okay, hi everybody. So glad to see everyone all suddenly. Okay, great. Yeah, I was going to talk about stellar nurseries in October skies because our next two events are in October. And so what are stellar nurseries? Well, many of the things that we see in the night sky through our telescopes or even just with our eyes are part of the life cycle of stars. And I just wanted to quickly go through that. This right here, oops, let me turn on my little thing that shows you where my cursor is. There we go. This right here, this star-forming nebula, that is a stellar nursery. That's where baby stars are being born all the time. And I'm going to quickly go through the life cycle. And so we see a lot of these. We're going to feature 4 of them tonight. Out of star-forming nebulae come open clusters and all different sizes of stars, from little tiny to giant. And more than 99% of the stars are the little ones that follow this pathway. And this pathway on the left-hand side, these stars will live for billions to trillions of years. Toward the end of their lives, they turn into red giants. And after the red giant phase, they eventually turn into a planetary nebula. All of this stuff is the carbon and the oxygen and all that other stuff that's formed inside of the star during its lifetime. And all of that gets recycled back into the galaxy to make more stars. And all that's left over is a little white dwarf. Okay, quickly going over to the large star. These are stars that are more than about 8 to 10 times the mass of our sun. These only last for millions of years before they turn into red supergiants. And after that phase, most of them go through a supernova, the explosion, which blasts all the stuff that they made during their lifetimes and during the supergiant phase. And all that stuff gets thrown back into the galaxy to make new stars from star-forming nebulae. And all that's left is a neutron star, and sometimes they just turn into black holes. So let me share with you a picture of one of the star-forming nebulae that we're going to see today, and that is the Eagle Nebula M16 that Jim Hahn, I hope you're here today, Jim, gave to us to share in the newsletter last month. Okay, so let's move on and see what area we're featuring today. And that is this area around Sagittarius, because we're about to lose Sagittarius in the night sky. So I wanted to quickly do this because it's a great area to see stellar nurseries. Here's Sagittarius. There's the body of the teapot. There's the top of the teapot. There's the little handle. There's the spout. And so, but these stars are really close to us. Whereas these nebulae that we want to feature tonight are quite far away. We'll get to that in just a second. This is the Lagoon, Trifid, Omega, and Eagle. They also have Messier numbers, the M numbers that we have. We've got M8 for the Lagoon, Trifid is M20, Omega is M17, and the Eagle is M16. And there's another very cool thing in this same area of the sky, and that is the center of our galaxy, this Sagittarius A star. That's the marking the black hole in the center of our galaxy. I have a little model of the galaxy back here. Perhaps you can see the black hole in the middle. It's not really that big on that scale, but there it is. This is an umbrella, and so it has that little dot there. But so, as I said, many of the objects that we see through our telescopes are part of the life cycle of stars. So we're beginning here with that star-forming nebula in the middle, big clouds of gas and dust. All right, so, and these star-forming nebula tend to be in the spiral arms of the galaxy where most of that gas and dust is. But you can't really tell, this doesn't give you a sense of the distance or the position in our galaxy of all this stuff. So let's move on to an overview of our galaxy. We're going to be looking carefully at this Sagittarius arm that comes around here and then runs between the sun and the center of the galaxy. And then this is the Orion arm over here. But up here is a little closer view of this little area that we wanted to feature. Here's the sun. I mean, this is not the size of the sun on this scale at all. You can't even see it on this scale, but the sun would be within that circle somewhere, just like the sun was inside of that circle out here. Here we are in our Orion spur, Orion arm. And very recently, back in August, a new study was published that combines the data from the European Space Agency's Gaia mission with data from Spitzer Space Telescope. And this little spur out here, they call it, it's like a little break in the Sagittarius arm that is sticking out, is newly discovered because the Gaia mission was able to carefully pinpoint the distance to the stars in some of these star-forming nebulae, and they learned that all 4 of the star-forming nebulae that we're featuring tonight are in this spur that goes off to the side of the Sagittarius arm. So now we want to get a sense of the distance and position in our galaxy. All right, here's the sun, I said. Now, all of the stars of Sagittarius are actually this close. I mean, they're within a few hundred light years of our sun. You'll notice these notations here. This line represents 2,000 light years from our sun, 4,000, 6,000, 8,000 distance. But the stars that we're looking at are very, very close in here, the stars of Sagittarius. They're so close, so we can see the individual stars. We need a telescope to see the stars and other stuff. So now, yeah, so let's take a little tour here. The Lagoon M8 is roughly here near the 4,000 mark. So is the Trifid Nebula, right in this same area. And the Omega Nebula is out here around 5,500 light years, out here, see on here. And then the Eagle, the M16, is out here beyond the 6,000 mark. Some other point I was going to make, but I can't think of it right now. But so from here, when we look at the stars of Sagittarius, these actually appear to be above the stars of Sagittarius. And where's the center of our galaxy? It's kind of off screen over in this general vicinity. The central black hole is right here. And so it's off over here a little ways. But if you want to read about that article that recently came out, just Google the Milky Way broke one of its arms. And you'll find the NASA story along with several other stories about the location of these guys and how they were determined. So it's really cool because I was going to feature these 4 star-forming nebulae anyway, and then I saw the article came in, and oh, right, let me include that, because you'll find it interesting if you want to take a minute to read it. So let's continue and go back and look at our field again. So realize how far away these 4 nebulae are, how incredibly far away the center of our galaxy is, and these stars of Sagittarius are right here in our front room, so to speak, and we can see the individual stars. So I hope you take some time at our next Society Observing Night. That's this Saturday. Don't miss it. And then 7 days later, the next Saturday is our public night. This, as you might notice, this is set for October 9th, our society night, if you look to the southwest. At that time, the Lagoon Nebula is about 20 degrees above the southwest horizon, just to give you a sense of how high in the sky you have to look. But I do hope you'll take a look at these and realize that you are looking at star factories, star nurseries, containing the raw materials produced in ancient ancestor stars that died over the last several billion years and are now recombining to provide the raw materials to make new stars, new planets, and potentially new life within the next few billion years. Enjoy your night.
Thank you, Marnie. That was wonderful. I really appreciate that. And everybody did. I have to turn my video back on. There we go. Uh-oh, we got questions. Okay, come on.
Okay.
Here. You have to turn the mic on.
Marnie,
Hi, Moon.
in the first picture that you had up,
Yes.
you had the littler stars that were shooting off going to the right,
Yes.
and the bigger stars going to the left. Was that just figuratively, not literally?
Let's see what you're talking about here. Let me see.
Hi, everybody. I miss you guys. The first page.
The first page, this one?
Right there.
So was that just to show the stars? They really don't go to the right and the left?
They don't move around like that, no.
I
This
just
is
wanted to
just-
make sure.
This is
I
just
just wanted to
showing
make-
the life cycle of the star.
Okay, all right.
Yeah. Thank you for helping with that clarification. Yes.
Well, Marnie, this is Ken. I have a question. Are there any other black holes in the galaxy that we can see, see where they are, other than the one in the center?
Oh, yeah, there's many that we can see the locations of. Actually, in Night Sky Network, if you go to the outreach resources, type in black hole star map, and you'll find star maps of where the black holes are that not can be seen, but you can at least point out where the locations are. Those are all stellar black holes. For the most part, they're stellar black holes. You know, the end of life of a star, of a massive star. See, there's the center.
Lee has a question. Hang on.
Yes.
So it looks like from that first picture there that you have the nursery, and
Yes.
on one side it goes to the sun type star, on the other side it goes to the giant stars.
Mhm.
What makes them go one way or another?
Oh, it's the mass of the star. The massive stars, the ones that are larger than about 8 to 10 times the mass of our sun, are going to take the supernova route. Anything less than that is likely to take the other route, the the sun-like star. In other words,
But
stars
it
that
came
end
from,
up
both came
as,
from the same nursery.
oh
well,
yeah, yeah, a star nursery makes all sizes of stars. That's another talk entirely, but yeah, all sizes of stars. You know, think of a rubble heap. You've got a whole lot of little tiny rocks and a few great big rocks. Same kind of thing.
Okay, anybody, no questions here? Anybody, let's see, I have to do this again. I'm sorry.
I don't see
apologize.
any in the chat.
Oh, okay, good. You can look. I can't because I need to.
Yeah, I know.
'cause you did it. Okay, all right. So anyway, okay. Well, thank you very much, Marnie. We all appreciate it. It's a wonderful talk.
No,
Good
thanks.
questions. All right, so for tonight's talk, I'm pleased to introduce Dr. James Erickson. Dr. Erickson has followed a career in robotic spacecraft at JPL for over 47 years. This has included work in both flight and ground system design and implementation, but he has specialized in the areas of operations design, implementation, and in-flight operations. Over those years, Jim has supported projects ranging from Viking, Voyager, Mars Observer, Galileo, the Mars Exploration Rovers, the Mars Reconnaissance Orbiter, and most recently, the Mars Science Laboratory. For the last 4 missions, Jim has had the privilege of serving as project manager for each of these during actual operations. He has 10 published papers and has received 2 NASA Outstanding Leadership Medals, an Exceptional Service Medal, and an Exceptional Achievement Medal. His hobbies include golf, amateur radio, urban search and rescue, and this may have been helpful, performing magic as a member of the Academy of Magical Arts at the Magic Castle in Hollywood. If we had a little magic, we might have gotten going here a little fast. Anyway, please welcome Dr. Erickson.
Well, thank you. I'm happy to be here, and I would like to say that it is a privilege to talk to all of you. This has been sort of a transition for me. I just recently stepped away from being the project manager and moved up, and now I'm managing all of the operations missions in the planetary science division here at JPL. But back to curiosity for the MSL. I have a presentation, and I will show you all the cool pictures, and I will talk quite a bit, and I will try and keep myself on schedule so that we can.
Hang on just a second, Jeb. Well, I guess you're okay. All right. It was telling me one thing and uh-oh. Did we lose somebody?
Can you hear me?
Yeah, I can hear you now. Good, okay.
So, can you see my presentation on the screen?
Yes.
Okay. So, Curiosity was landed on the surface of Mars almost a little bit more than 9 years ago, August 5th, 2012. And its purpose was to identify a region of Mars that was a potential habitat for the past or present, where some organism could exist if you dropped it into that environment. And so to do that, we looked at biological potential, obviously geology, geochemistry, water in particular, weather and climate, and radiation levels and hazards. And that's sort of a sideline having to do with some of the human program requirements that we were levied on. But the water, weather, and climate are all things that we are understanding, not from looking and finding water or watching the clouds and the climate, but actually from looking at the rocks that are left over from the formation of the crater. So what do you know how do you know if something is a habitable environment? it has to have a persistent liquid water, and it has to be nice water. It can't be too acidic, can't be too basic, can't be too hot, can't be frozen. So it's got to sort of be in the sweet spot. Then it's got to have key chemical ingredients of life. It's got to have sources of carbon, hydrogen, oxygen, nitrogen, all of those, potassium. And one way or another, it's got to have energy for metabolism. Now, for really primitive organisms, that can be as simple as ingesting two different minerals and exchanging an electron from one to the other and absorbing the energy from that. And that is what feeds very, very simple organisms here on Earth, and could do it on Mars as well. Having a little bit of trouble. It's not, okay, I'll just do it that way. So where we are is a place on Mars called Mount Sharp, which is in Gale crater. Now, Mount Sharp is what we actually call it when we're speaking among the cognoscenti, those of us who are working on the mission. And it's really got 4 different really interesting locations. It's got an area that is what we call the Murray Formation, which is at the base of the lowest part of the crater. It's got a hematite-bearing ridge. It's some clay areas where it's a lot of clay minerals. And then finally, and this is important, the sulfate-bearing areas. And the interesting thing is, from clay areas down, those were all formed when there was a very habitable Mars, lots of liquid water. And then suddenly you switch to sulfate depositions, which aren't formed when there's water available. And that transition from a wet Mars to a dry Mars is one of the most important things we're probably going to be finding now. We're just in the area in between where it's clearly clay bearing, and we're about almost convinced that we're seeing some of the sulfate that we see from orbit. And so in the next few months, we're going to be getting some good exploration, except we're going to take a short break and give the rover some time off, because Mars is going behind the sun as viewed from the Earth. So while we're in solar conjunction, we put it on autopilot, let it sit in one place as safe as we can make it, because we can't talk to it for that 2.5 week period. So these are some of the instruments that we're going to be exploring Mars with, and have been for a while. Everything from obviously a lot of cameras, whether it's the mass cam, a camera in the belly that looks straight down, a camera on the end of the arm, the MOLLE, cameras for navigation, hazard cameras, 4 in the front, 2 in the back, 4 in the back, and we use 2 at a time in front and 2 at a time in the back, with spares in case something goes wrong, because the hazard cameras are how the vehicle tells itself that it's safe or not. We've got a mineralogy experiment called CHEMIN, Chemistry and Mineralogy. We've got SAM, which is spectrometers at Mars. And spectrometers and spectroscopy is something you're going to hear quite a bit in this presentation, because that's how you tell what things are when you can't break them apart with your hands and put them in any kind of an instrument, or do reagent testing to see what's in them. We have a device called the DAN, which actually can fire neutrons into the surface and look at the reflections from what's there and understand whether or not you can see hydrogen. And when we see hydrogen, that mainly means we're going to see either water or ice, because that's it's looking for hydrogen that isn't bound into a mineral. We have a weather system called the REMS. And as we talked about before, we have a chemistry instrument actually on the arm itself, the APXS, where you can actually put it up against a rock and use it to fire protons into the rock and look at the X-ray spectroscopy from it and get a reasonable idea of what are the elements of the rock. And we just went through most of that. But one of the things that we didn't go through is, okay, yes, you know that we're drilling into the rocks. And somehow we take that material that we've drilled and sift it down so that it's got the right size particles that can be put in either the Chemin instrument, which fires lasers at the material and looks for X-ray spectroscopy to determine what the elements are, and into SAM, which has 4 different spectrometers, including a gas chromatograph, a tunable laser spectrometer, and a couple others. And the device that does that sifting is called the Chimera. And we use it every time we drill a hole. We prepare the material with it, and then we drop it into the 2 sampling instruments, SAM and Chemin. This is what it looked like pretty close to the last time it was at JPL. The only thing different between what it looks like now and on Mars is on Mars, we've already put the plutonium RTG on the back, and it's getting its power from there rather than the cable you see them working with. Now, I talked to you about the belly pan that's underneath the rover looking down. On the way down, we used it to take pictures of our descent, including interesting things like when the heat shield came off, we watched it go down, and not just because it was a cool picture, but we could tell how fast it was spinning. And that gives us more information about how really effective our heat shields and our whole system of getting from space onto the ground really works, and whether we're right on the edge of losing it or we have a very robust system. And so that's some of the data that we wanted to take. We use it now by actually, when we drive around, it's just continuously taking pictures looking straight down, and we call it the sidewalk imager now because of that, just like you're looking straight down at the sidewalk. August 5th, 2012, first picture. Time to see where we would go. Back on Sol 84. Pretty clean looking. Now you can tell it's been around on the right. 9 years, you accumulated a lot of things, a lot of dust on a lot of the rover, but not all of it. The RTG always stays clean because the radiation tends to repel dust particles. When we first landed, we landed using rockets to slow our last final descent for touchdown. And one of the things that it did was it got rid of all the dust in the local area, so we could see the rocks and that were there without them being obscured by dust. So we got some quick samples in the first couple of days. Some of the things we saw were very round pebbles and sand. And these kind of conglomerates aren't going to form unless they're in water that's flowing enough to tumble the pebbles to make them round, and then also have enough water at some stage in the life to begin the cementation project of putting the different types of rocks together. And then Yellowknife Bay was one of the first areas we explored. This is an area where there were, from orbit, 3 different rock types that came together, and it meant that we could go to one area and get a wide sample, 3 different looking materials at least. We went there, and in the first 90 days, we actually found our first habitable environment here at Yellowknife Bay, where we found everything we needed to say, if you took an amoeba and dropped it into that water, it would thrive. So we can't see if there ever was any life there, but if it was there, it would have thrived and grown. So that means that at least one checkbox that it had a time when there could be something that could live. So this is what the drilling system looks like. The drill's in the upper left. It's a hammer drill, so it's not like a spiral drill that you would see there. It's more like a rotating chisel being pounded on by somebody. And we work our way into the ground. And this is the practice hole on the right, and then the first real science hole in the middle here. And that's the kind of material you get. You'll notice that there's a big distinction between the reddish Mars dust that you see everywhere on Mars and the actual interior of that particular rock, which is very much a grayer rock. To the lower left, this is a scoop where we can actually, after we've ground up the material, we can move it into the scoop and then open it so you can look and see whether it's the kind of powder that we believe we've created or not. And if it wasn't done right, we could dump it out and try again. And we can also take that scoop and actually use it if we're like in a sand pile, scoop some up, put it back in the instrument, and then do the sifting and deliver it to the two in situ instruments. Now, this is a little cool. These holes are about the size of a dime. But when you look at the side of the hole, you can see two obvious things. One, there's these swirling white patterns, which are just inclusions in the rock. It wasn't just a solid material just of one kind. It had veins running through it that water flowed in and deposited other material. But you also see these black dots. And that's one of our cool instruments that does imaging, but it also fires a laser and does laser-induced breakdown spectroscopy. And you look and say, well, that's a dime. Those holes are spaced about the thickness of a dime apart. And so you'll notice that one of them, second from the bottom, actually hit one of the sulfate veins, which is how we know that's what it was. And all the rest gave us the actual rock kind. So that was not exactly fortuitous because we were trying, and if we'd failed, we probably would have taken another couple shots at it. But that's the kind of a thing that we can do with this. From 10 feet away, we can identify to a large extent what the material is we're looking at. Okay, so once again, we checked off all the boxes. We had water, we had the key chemical ingredients, and we had the source of energy. Now, in the upper right-hand corner is where we see what X-ray diffraction pattern looks like in our Chemin instrument. Basically, it makes a ring, which is the angle between the angle that it's being reflected back at us. And depending on where it is, it tells you something about what is the material that's there. Now, phyllosilicates are a fancy word for clay minerals. They like to use that. It's very specific. We tend to just use the words that we're most comfortable with, and clay minerals happens. Then that gave us the information about the rocks and what the environment was like, because clay minerals form when you have liquid water of reasonable constituents, not too acidic, not too hot. It's not boiling and it's not frozen. So that check that box. In the lower right is some of the information from the SAM. Now what SAM does is it takes those powdered chemicals that we've drilled out of the rock and it puts it in a little container, and then it moves the container into this oven, which can heat up to 800 to 1,000 degrees centigrade. And it breaks down the rock, and it can then measure what the gases are that are coming off the rock at each of the temperatures. And when you do it right, you can also tell how much water or whatever the gas is comes off that. And then graduate students take all of this information from SAM, put it together, and come up with hypotheses as to, well, if it's got this amount of oxygen, this amount of CO2, this amount of H2O, this amount of sulfur dioxide coming off at these temperatures, what are the possible minerals they could be? And come up with the answers, and then defend it in front of their peers. And we treat that as the answer. But once again, it was perfect. It wasn't too salty, wasn't too acidic. Everything was great. So everything we saw there suggested that the John Klein site, which was the first one at Yellowknife Bay we studied to find this, it was either at the end of an ancient river system or within an intermittently wet lake bed, something like the dry lakes that you see out in the Mojave, where in the rainy season, it's mud and then it dries up every year and continues like that. Indications of sustained interaction with liquid water, low salinity, not too acidic, and it wasn't strongly oxidizing. So it wasn't too energetic and ripping apart things. So if there were organics, they would not be destroyed instantly. And then the key chemical ingredients we talked about, and the presence of minerals in various states of oxidation, which could provide a source of energy for primitive organisms. I talked about ingesting two and then donating an electron from one to the other, and the extra energy is what they absorb. That was all there for it. So this was a home run right out of the box. And then we went exploring. We had lots of challenges. Shortly before this, we found out that we were in an area that had really, really sharp rocks that were damaging our wheels, and we were needing to do something about that. And so we picked our way very, very carefully out of that area, and we've been driving extremely carefully ever since. So we think we've managed to control that, and we believe that the wheels are going to last longer than the rest of the vehicle now, which is a good thing. But one of the places we came to that if we couldn't have done drive over it, we would have had to have detoured back into the danger area and quite a ways around our route. But we tested it out and then just drove up the sand. Now, that doesn't sound like much, but you realize if we did get stuck in the sand, there's no AAA. There's no way around that. And in fact, that's how one of the MERS died. The earlier Mars exploration rover Spirit died because of that. So that can happen on Mars. Okay. We call it the Kimberley. It's named after a location in Africa. We actually name a lot of these areas after different parts of the world where there is interesting geology. And so there's an area of Scotland that contributed names for some of the things, and a lot in Africa where we do a lot of the oil geology, which is also where you get a lot of field geology done. And these are all sandstone beds, and they've been tilted for one reason or another. Earthquakes are a possibility, just like they are on the Earth, and maybe some other features. Like sometimes you get things that look like they're tilted because it's in very, very slowly running water, and soil is being transported down a very slow river, and it falls downhill. And then when it becomes a rock, it looks like it's tilted, when in reality, that's the way it was formed. So, an example of that, we believe that these were lake deposits at the base, but they came from rivers that were elsewhere in the crater. And whenever you have enough rivers, you're going to get delta areas where they meet into a lake, very similar to the Mississippi River Delta, if you've ever seen that from an airplane. And you can get different types of deposits. The ones I talked about earlier are the delta deposits that are at an angle. And you can get a lot of lake deposits which have less angles down to basically flat. And it's all driven by water. So there's a lot of water coming up. And so filling up the crater is happening by water deposition of these lake deposits. So far, we've gone traversing over 460 vertical meters. We've done about 26 kilometers of horizontal traffic across in order to do that. And primarily, it's made out of fine-grained, finely layered sedimentary rock, like we said, formed from mud in ancient lakes. And the mud cracks that you see in the Mojave Desert are replicated here. And obviously, in this case, they had periodic dry areas. And there was times when it was re-wetted and deposited different minerals in between in the cracks. And we see that in the Mojave as well. And we get it at a different scale where fractures in the bedrocks can be filled with veins of minerals that flow through, and they aren't tiny like that, they're larger. And you see all the different sizes, even getting deposition after it's hardened into the rocks, and there's cracks that are available to fill up. Now, after the lakes disappeared and the climate became dry, sand dunes covered the area. That drifting sand and blown winds scoured the area and got rid of a lot of the material, but some of the material was protected by capping stones, capping rocks that are visible on the left and off to the right as well. And that means that since they didn't get eroded, they form these little buttes like you see in Utah. For much the same reason, there's a harder rock on the top. And you say, well, why are they able to survive? And the answer is, these were just better protected by random chance. There's nothing special about those rocks. The rest of it was there too. Now, you'll only see 32 holes here because on the weekend, I had to quickly change the number from 32 to 33 after we did our last hole, but I didn't have a picture I could include yet. So we're doing well. We have a lot of samples to tell what Mars is doing to us, and importantly, in all the different 4 major types of regions that we see in Gale Crater. Now, this is where it gets interesting. We're going to talk about what we can and cannot tell. We can't really find long chain organics and tell what they are. One of the reasons is the materials that we're using and the instruments, in the case of SAM, require that you bake the rock. And if you have long chain organics that manage to somehow survive, they'll be just ripped apart. Now, they will leave smaller chains as leftovers. And so graduate students get to look at the small chain organics we find and try and figure out what they could have been ripped apart from. Meaning, if there was a really long chain organic, like something like life, and it went through the process that we use to detect it, it would be broken into these little things. But by getting enough of them and the right kind, you can make a good guess as to what it was made out of originally. A much longer chain organic that you can't detect this way, but you can assemble the evidence that it was really there. Now, one of the things that happens when you go for millions of years is some of the minerals replace maybe carbon bonds with sulfur bonds. And they're much stronger and they resist the heat issue much better than if they did not have a little bit of sulfur in it. So that also helps us. Okay, now a little bit about Mars itself. If you look at Los Angeles as an example, you'll notice that it's, somewhere between 7 and 20, maybe 30 degrees on a really bad August day. But it's a very small swing in temperature. Mars, it's different. With only 1% of the atmosphere of the Earth, it's a very, very wide swing. You're talking about somewhere close to 60 degrees C, plus or minus. But it's also from, if you're lucky, minus 10 C down to minus 100. So things get dicey and it's a really bad place to live. This is a little bit interesting. We've seen these with the MER rovers, Dust Devils. They got a lot of movies of that, and we're seeing it here too as well. The sad part is just about 100 kilometers north of us is where the InSight seismometer instrument was deposited, and they're solar powered. And if one of these was near, it would be cleaning off their solar panels and they would be getting a new lease on life. Unfortunately, they're not seeing it. They're not seeing anything like that. They can't see them visually when they look, and they just aren't getting any cleaning deposits. So they're only going to make their plan, not get any bonus gators. We also look at the atmosphere, looking at some of the clouds. Clouds on Mars are either water or frozen CO2. When you look at them, they're very thin. Small ice particles results in what we call iridescence. And you see that at the lower left, and you get diffraction of the sunlight through it. And it's pretty cool. You do have to really stretch it to see it. Meaning we take the images and we make the whites whiter and the colors more colory to see the difference in the, it's not truly what you would see. You would basically see the view that you see now with the rocks and the very much gray looking clouds. And now here we get to some more controversy. When we looked at some of the atmosphere of Mars from orbiters, either the European trace gas orbiter or some of the earlier ones, and some of the Earth observations, sometimes people detected a little bit of methane in the atmosphere, and other people did not. When we got there, this is what we saw, where we had quite a bit of methane. And it changed throughout the year how much. So that in spring going to summer, it's at a low point. And then as it warms up into summer and starts to go into autumn, it's at its maximum. And then it continues this cycle year after year, with an occasional giant burst, like you see in the upper right-hand corner, which is out of step. Now, it's best explained as the seasons are heating up the subsurface, and when that heat gets down below, it is able to melt ice that's down there and let it seep out, where it'll eventually both bring water to the surface, but also bring methane. The occasional large spikes have to be something different, and we don't know exactly what it is. But somebody finally figured out why we see all this methane, and the TGO measurements didn't show it. We're looking only at the really bottom of the atmosphere. We're getting samples that are no more than about a meter off the surface. TGO doesn't look that far down in the atmosphere. It can only penetrate to the 80 kilometer and higher. Below that, it just can't detect it. So somebody realized, well, probably what we're seeing is this stuff dissipates rapidly, and it's coming out in the daytime when we make our measurements. So we decided to do a bunch of measurements at night. And even when we went day sample, get the high methane, nighttime, get no methane, next day, high methane. And it was consistent. So that's what's going on. Real close to the ground, the methane doesn't mix as fast. We get a chance to detect it, but after only hours, it's gone. So that's an interesting to happen. Now, the controversy is there are two ways that you can have methane gas produced. One, obviously, is a biogenic mode, but there are others that can take different rocks, like serpentine in particular, and in the presence of water, it'll dissolve out some chemicals and release methane gas. And that is a possibility for what's going on here. And there's also the possibility that there's a biogenic source under the surface, and we can't tell the difference. Methane's methane. So we won't be able to answer this question. Now, I talked about radiation as part of the human program. And what we did was we measured radiation from the sun and occasionally cosmic rays by this instrument. And when you take a look over the course of the 500 sols on the surface, if you were an astronaut and you went to Mars, then landed and stayed 500 sols and then came back, you would get 1 sievert, which is all an astronaut is allowed to do in his lifetime. So we have to solve this somehow. We just can't have that kind of a environment for humans. So one of the things we did was say, well, people are talking about using the rocks on Mars and maybe putting them over a small building and using it as shielding from the radiation. And in order to figure out how effective that is, we went up and in the part of the day when the sun was shining and kind of got into the shaded aspect of a big rock outcrop and did radiation measurements there and radiation measurements after the sun was shining from the other direction and getting the radiation from the sun. And they were doing is just characterizing how effective the rock is going to be as a radiation shield. So lots of things we're doing. Okay. We're coming from the lower right, and the current location is a little bit off now. We've moved a little further to the right path, that wandering, meandering path you see us taking. And we're heading towards what they call the green hue pediment, which is where after the main rock formation had been scoured out into almost what it looks like now, something oozed, erupted, or flowed up onto the surface, partially covering some of this. We don't know how much, because when we went up close towards the middle and a little bit to the right in the lower area between the green and the blue is what the pediment is. And we looked at the rocks that were there, and it was clearly eroded away. We just can't tell how far away it was eroded. It may have been a massive structure that over time, this is all that's left, or it could be just a little bit bigger than this and the sides are gouged out. We'll find out a lot more when we actually continue our meandering path and drive up onto the pediment and do a lot more measurements when we're there. And then finally, towards the end, we're going to take a look at the Geddes Ridge, which is what's in the center, go up the channel as far as we can so we get to where there's nothing but dust covering everything and it's too deep for us to drive up. And that'll be where we either turn around and do something like go back and see some more interesting things, or we end the mission. Right now, we're exploring that, like I said, the transition between the clay wet generated units to the sulfate bearing units, which are the no water situation. And we really want to try out, figure out not only was that really what's going on here, but also if we can figure out how fast it happened. Did it take millions of years, or did it take hundreds of millions of years? And if we can figure out that, we can maybe make better hypothesis of what it is that caused the water to go away. Now we're going to take a left turn and tell you a little bit about what we have to do to make this work. First off, challenges are the Martian day is a little bit longer than the Earth Day, about 40 minutes. So if I come to work on Monday at 8 o'clock, Tuesday it's 8:40, Wednesday it's 9:20, Thursday it's 10 o'clock. And pretty soon you've gotten to where you get up at 3 in the morning, go to work and come back there. And the reason is the rover has to operate during the daytime when it's on the warm part of the Martian day. If it's at the -80, it's too cold to move anything, and the vehicle can't do that. So we do all our operations between, probably mid-morning to mid-afternoon. And so in the early morning, we send up the commands to the vehicle as to what it's supposed to do that day. It's really more like a computer program laying out the activities for the day than commands per se. And then it'll do its thing. And the last thing it does before it goes to bed is send the information about what it did during the day back to the Earth. And then on the middle left, we get that downlink during the night. We take a look at it on the Earth and plan what to have the rover do next. Is the vehicle in trouble? Did it run out of time? Did it get hurt? Did it execute everything perfectly? What data did it get? Do we have pictures of where we're going to go next? And they then decide what to do with the capabilities of the vehicle, with the power that it has left over in the batteries and what it's going to generate from the RTG, the images that we're going to decide where we're going to drive to, if that's what we're doing. And we build a package, send them up, and start it all over again. And while it's busy working, we're busy sleeping, and it's sleeping when we're working. Except every so often, it all syncs back up and we're on daytime and they're on daytime. And that's actually not a good time, because what we'd like to do is always be on the opposite of Mars. When it's daytime there, it's best to be night on Earth. Okay, and then finally, another description of the cycling. And this is just to show that it's a continual process. It takes about 8 hours to do all of the work that the operations team has to do in order to get the uplink ready for it to be sent up to the rover. And this is the wonderful people that do it, along with about 500 scientists scattered across the world working on it. We have instruments from France, Germany, Canada. We have Russian, and we have some from Goddard Space Flight Center in Baltimore. So we have a wide variety of people supporting us, and we have sort of the best deal, because everybody else in a different time zone has to match ours. And so, like, some of them have been working on a program that's 8 hours difference from us for years and years and years. And it must be rough on them. But I appreciate all of them. So, and I think that's where I'll end it. Thank you. And we'll have some time for questions. I hope that I didn't go too long.
Thank you. Thank you, Jim. Now you timed it just perfectly. It's right now exactly 9 o'clock. We need to have some questions, so hang on. Let's see if I can get my glasses so I can see what I'm doing. That always helps. I can see what I'm doing in the dark. The only thing is, nobody else can. See, I don't know if I can actually do this safely. Yeah. Somebody says it's a lot bigger than I thought. Yeah, it's not a small craft.
It's about the size of a Mini Cooper, if you know what that is. Not a really large car, but bigger than a golf cart.
Mm-hmm. Wow, that's a
How does it take a selfie?
Well, remember I talked about the camera on the end of the arm, the Molly? What it does is it basically stretches its arm out, points it back at itself, takes a picture, moves very slowly over to the other part, takes another, takes another, takes another, goes down, takes another, another, and builds up a giant mosaic of little tiny images from the end of the arm. When we put them together, it kind of looks a little weird because it looks like the arm is cut off. Because obviously, if we want to take a picture of the rover, we move the arm so it's out of the way when we are looking at that part.
Okay, well, Dave's working on it. How long will the fuel last?
Well, the only fuel we actually have is the plutonium inside the RTG. And it's decaying at the normal rate for 82-year half-life, something like that. And it looks like we're going to start having trouble in 5 years or so, give or take 2. And at some point, 2 years later than that, we probably won't be able to do anything. So somewhere between 5 and 9 years, I think, from now is where we're going to be.
There's a Zoom question here that says, what's the prevailing theory as to where the water went?
Well, most of the theories I've seen in one shape or fashion rely on what we call dissociation. Somehow the water is transmitted to the upper atmosphere and radiation from the sun breaks a water molecule into hydrogen and oxygen, and the hydrogen and the oxygen are kind of blown away because they're now lighter, and the solar winds can move them away from the planet out of the planetary orbit. And that sounds like a very slow process, but one of the things we're trying to find out is how fast the water went away and whether this is actually a theory that can account for that or not.
And that's a function partially of the fact that it's virtually no magnetic field to shield the planet, right?
That's right.
Yes. Okay.
Although we have detected a remnant magnetic field, a leftover
Yeah.
that's been embedded in the
Not
rocks.
Not nearly strong enough to hold off any solar wind effects, for instance.
Correct. You can barely detect it with the instruments we have that are on the ground.
I have another question here from the audience.
Hi there. I was just wondering if you could talk a little bit about the communications. Does it beam directly from the vehicle, or does it sort of have an uplink to an orbiter, or how do you get data back to Earth?
That's a great question because we use all of the above. We have a UHF radio system that can both transmit and receive from the various Mars orbiters, both US ones, European ones, and we also have the ability to talk directly to the DSN and other similar radio telescopes here on Earth, both getting commands from the Earth and sending data back to the Earth. Now, our data rate from Mars to the DSN is pretty low, hundreds of bits per second, while up to the orbiters, it's in the neighborhood of 2,000 bits per second. And they have giant 10-foot antennas and much more powerful transmitters, so they can get it to the DSN, and they take all our days worth of data, and at least the one that I asked for, it took the transmission time from the rover up to the orbiter took about 10 minutes, and from the orbiter to the DSN took about 3 seconds. So 3 seconds for the whole day's effort.
Thank you. Appreciate it.
I'm pretty sure I understood that there was a problem with the drill for about a year or something, and then it you were able to get it working again? Could you talk about that a little bit?
Sure. What happened is, in the original design, the drill bit was stabilized by 2 prongs on either side. And then we would gradually lower the drill into the ground and drill, and then raise it, turn it up, and put the material into the sifter. Well, the motor that was driving the drill down into the ground got stuck. It gradually failed and would not move the vehicle. So on pretty much its last gasp, what we did was we stuck the drill all the way out. And now we don't use those stabilizer prongs. Instead, we very carefully move it into contact with the ground and then gradually apply the right force onto the drill while we're drilling to actually get the drill. And that moves the material into the drill. But unfortunately, it can't get to that device that I just talked about, which is the sifter, because that required the drill to be retracted all the way so that the hole for the sifter matched the hole in the back of the drill. So instead, what we do is we then take the drill over to one of the instruments that we have and hold it over the cup and reverse drill and let it fall out of the drill into the sampling mechanism for both the Kemen and the SAM. It took a while to figure out how to make that all happen. And that's why we lost about a year. Now, we didn't lose it. They had lots of other instruments that were working overtime, and some of them were a little sad when we got the drill working. So they didn't get as much time. Okay, next.
Okay, I think we're out of questions here, and I don't see any more in the chat. So does anybody have anything else they want to ask? No, that's it. Oh, another one. Come on. Come on.
So nothing to do with curiosity, but this was with Spirit and Opportunity. It had solar panels. And one of the problems was dust collecting on the panels and limiting the power output. Is there any thought to putting wipers on it?
That's usually the first thing that happened. It's very difficult because the dust is sticking to the material. It's like electrostatic charged, and it is hard to move it. So there's been 2 different ways it's happened. It's been removed by the dust devils that have enough force to drive them off, or it's been removed in the case of the InSight mission. They actually dug up a bunch of rocks. That's not quite fair, but sand particles, they scooped it up and they dumped it on the solar panel. The solar panel that they have is tilted a little bit. And when these sand grains and things rolled off the solar panel, they also scoured clean the panel of the dust. So they got a decent bump in energy, like 10% when they did that. So they did it a few more times. And when they come out of conjunction, they have a big challenge ahead. Do they want to spend their time and energy trying to clean the solar panels more that way? Or do they want to take science data? And it'll be interesting to see what the science community decides. One way or another, they're going to be running out of power in the coming year or so.
Yeah, it always seems like on missions like that, and unless you're really not planning on being there very long as far as operations, but it always seems like we want to have them run longer than they're designed for. But it seems like the isotope generators are much preferred for doing anything like that.
Yeah, it kind of depends on how much energy you need. And the other thing that makes this last longer is It's just like a car. You buy a car from a dealer, it has a 4-year warranty. That's the equivalent of the deal we make with NASA, that we're going to build something that we are pretty sure is going to last X years, which means we have to make it so we really think it would last a lot longer.
Mhm.
And they understand that, and that's just a fact of life.
Okay, it looks like, I think we're done for the night. Thank you very much again, Jim. We really appreciate it. Lots of good questions and lots of good information. And we're glad that that's still running up there, still collecting data. So congratulations.
Thank you. And it's
Okay.
nice to have a sister join us.
Oh. Somebody has their hand up, Sean. Let's see, what does he want? Hmm?
Just clapping.
Well, that was a clap.
Great
Oh, that's
presentation.
right. Yeah, I forgot what the icon, I don't know what the icons mean. I don't know. It's a problem with icons. Anyway, okay. Well, I think that concludes our meeting for the night, and we really appreciate you guys coming in, and we'll see you next time. Again, I'll remind you that next month's meeting will be live only. We won't be able to Zoom because there'll be information that he won't want to have recorded, and there's no way to secure that without not Zooming. So it's going to be here only. Thank you very much.
Can I ask a question what the next talk is on? What's the next talk?
Oh, well, let's see now. That should be upcoming in the newsletter.
Okay, thanks.
The newsletter will be coming out shortly, so she will have that information for you.